you haven't gathered from what I'm passing out here and from your first Socratic app question today, we are heading in the direction of chemical nomenclature. Chemical nomenclature. And the term nomenclature simply refers to a systematic method of naming. So again, chemical nomenclature, the systematic method of naming. And chemistry has its own set of nomenclature, but chemistry is not unique. I mean, almost any discipline has their own set of nomenclature. For example, if you go into English, you talk about verbs and adverbs and adjectives and, yeah, well, see, I wasn't an English person. But again, there's things that describe what those things are. If you go into biology, you'll use things like dorsal and ventral and anterior and posterior. And typically outside of biology, you don't hear those terms. You'd hear more like front and back and top and bottom. Well, chemistry is the same way. We have our own set of nomenclature. And before we do that, let's see how we did on this app question. Question was to see how many oxygen atoms there are represented in this formula. And that would be 8. And how did we arrive at 8? Two times 4. 2 times 4 is what we wind up with. So when we see a quantity in parentheses, we interpret the formula. That means that you're taking that unit in parentheses and you're repeating it twice. So if you wanted to visualize this one, the formula, you would think of it as, again, we'll put this up here. So we have Ca3PO4 in parentheses 2. You can think of it as 3 calciums, and then you can think of this unit of PO4 being repeated twice. And of course, each one of these means that there are 4 oxygens in there. So there's 4 oxygens here, 4 oxygens there, for a total of 8 oxygens. So now when it comes to chemical nomenclature, there's a few things that annoy students a whole lot. And that is, as we already talked about with the elements, spelling counts. Spelling counts. And spelling counts simply because of the way that we write names. For example, we could have something like chlorine, chloride, chlorite, and chlorate. And probably not by the end of the hour today, but certainly by the end of the hour on Tuesday, we should have a pretty good ability to distinguish between each one of these. Right now I'm going to tell you what the difference between them is. Chlorine you should already know because we did this before the exam. Chlorine is one of the elements that we say is a what type of element? Diatomic, which means its formula is Cl2. When we talk about the chloride ion, when we talk about chloride, we're actually referring to the chloride ion. Its formula is Cl with a negative charge. If we talk about the chlorite ion, its formula is ClO2 with a negative charge. And the chlorate ion is ClO3 with a negative charge. So again, when we look at these, you notice that as we go from one to the next to the next to the next, each of these differ by only one letter, and that different letter conveys a different meaning about its composition. So again, unfortunately, spelling counts. When we write out formulas, the number of atoms count. We need to be able to count number of atoms. So if we look at something like this, we'd see very clearly that there's 3 calcium. How many phosphorus would there be? 2. And then again, there's a total of 8 oxygens. So we should be able to read chemical formulas and see where they lie in terms of number of atoms of each element. Now there's 2 main types of compounds we're going to be looking at. And I should talk about, first of all, you have two handouts there that I passed out, and real quickly what they represent. And I should be able to go back here now to your content section. You will always find whatever I pass out in class in that content section of your D2L course. You'll see today it's listed for September 15th. So your polyatomic ions. This here is a list of ions that you need to memorize. There's a list of ions you need to memorize. And I would contend that as far as memorization in this course goes, most of the memorization occurs at the beginning of the course. You've memorized the names and chemical symbols of the elements. You'll need to memorize these. And part of that is as we go through the semester, if we talk about something like sodium phosphate, you're not going to have time all the time to pull this out and look it up and then try to figure out what that formula is. It's something that you need to get to the point, kind of like if I said 2 plus 7. Everybody right now, if I said 2 plus 7, is going to say that is 9. And you need to get to that point where if we said the formula of sodium nitrate is, you should be able to respond almost just as fast to say that that is Na3PO4. Now you're not there yet because you don't know the polyatomic ions. But at the end of the course here, as we go through, starting probably about 2 weeks from now, if we talk about the name of a compound, it's going to be assumed that you know what that formula is, just like I assume that you know what 2 plus 7 is right now. I didn't tell you that 2 plus 7 was 9, but again, you know what it is because you've been practicing that, and you'll be practicing this nomenclature as well. Now, part of the reason why we need to memorize these, it's unfortunate. I say, couldn't we make a simpler set of rules for everyone? In other words, if we look at these, first of all, if you look at these polyatomic ions, if we were to analyze what polyatomic means to begin with, the prefix poly means many. So these are many atomed ions. These are many atomed ions. And what I thought was, wouldn't it be great if, for example, we see all of these end with ATE, if all of them that end with ATE had the same number of oxygens, but they don't. You'll see that the phosphate and sulfate here have 4 oxygens. The chlorate has 3 oxygens. Carbonate has 3 oxygens. If we go up to acetate, we see that it only has 2 oxygens. Now there is a reason behind this, and the reason is historical. And what happened was that when scientists first started working with these substances acquired some common names. And it just so turns out that if we find sulfur out in nature, and by out in nature that means if we found some rocks and we started digging up compounds containing sulfur, it turns out that the most common arrangement we see is with 4 oxygens for every 1 sulfur. And so that historically was called sulfate. If we find phosphorus out in nature, we find them as phosphates. If we find nitrogen out in nature, we find them as nitrates. Now there are other forms, but they are the most common ones. So because they're the most common, they were the first ones that were first defined and described. It wasn't until later then that we found out that, well, the phosphates had 4 oxygens, but the nitrates only had 3 oxygens. By that point, we already had this habit of calling these by the names, and it didn't make a whole lot of sense to change the name. So what we had to do then is that once we learned the chemistry behind them, we then had to adapt a set of rules that fit what we had there historically. So that's kind of where it all came about in terms of why there's no recognizable pattern. Now there is actually some pattern if you look for it. For example, if you look at all of them that end with ATE, what do all of them that end with ATE have in common?
They end in oxygen.
Right, they all do have oxygen. So anything that has an ATE suffix, and that's your first point here today, anything that ends with an ATE suffix. See, I know that English. Suffix means it comes at the end. How about that? I'm so proud of myself. So, if it has an ATE suffix, that means it contains some oxygen. What else do all of them that end with ATE have in common?
A negative.
Right, they all have negative charges. Now some of them have a 2 negative charge, like sulfate. Some have a 3 negative charge like phosphate. Some of them have a single negative charge like nitrate. So that's probably the number one thing when you look at these. If they have that ATE suffix, that means that they have oxygen in them and their charge is going to be negative. The only positively charged polyatomic ion you'll be memorizing is called
Ammonia.
the ammonium ion. That's the ammonium ion. And its formula is NH4 with a single positive charge. And then we'll talk about why these three common metal ions over here, because you say, well, cadmium, that doesn't sound very common. That's because we're going to be looking at a set of rules that helps us determine charges for most of them. Again, right here, most of them are based on their position in the periodic table, but there's a few of them where, based on their position, we don't know their charges and they need to be memorized. Now, you are going to be responsible for some polyatomic ions beyond these, but we'll talk about that when we get to that here towards the end of the hour. For right now, we're going to talk about the types of compounds, and the types of compounds that we'll look at are ionic and molecular. And we're going to make a very quick, small table here that helps us distinguish between these two. First of all, if we have an ionic compound, ionic compounds involve metals bonded to nonmetals. And this is going to be with one class of exceptions. Exceptions are always fun. And those exceptions are going to be ammonium compounds. Over here on the molecular side, this would be either nonmetals and or metalloids that are bonded to or bonded with other nonmetals or metalloids. Now, going back to the periodic table, I'm going to ask you here to get your periodic table out because we are going to be writing on that periodic table today. And you can never have too many periodic tables. Anybody need a clean, fresh one today? All right, pass that down. Two. Anybody else? 1, 2, 3, 4. 1, pass it down. 1, 2, 3. Right, everybody here. Anybody else need one? Okay, we're going to be using a lot of periodic tables here for the next couple weeks as we learn some charges and so forth. But as a quick reminder, on our periodic table here, where do we find the metals? What separates metals and nonmetals? The double line, exactly. We got that staircase there that separates the metals from the nonmetals. So basically, if you have elements from over here combining with elements from over there, we're going to have which type of compound? Ionic. And if we have a molecular compound, molecular compounds will be elements that are located pretty much where? Over here. Because metalloids are ones that lie right along the staircase, and then the nonmetals are the ones that are to the right of that staircase. So again, molecular compounds are ones which are concentrated kind of on that right-hand side, more up towards the corner. Now the other thing is here is we say that in ionic compounds, we say that atoms are joined by ionic bonds. And all we really need to know about this right now is that in these here we say that electrons are transferred. And in molecular compounds we say that atoms are joined by covalent bonds. Atoms joined by covalent bonds. And this means that electrons are shared. Now that's pretty much the extent to which we look at bonds right now. Bonds will be covered in detail in your text in chapter 10. So we're about 5, 6, 7 weeks away from that yet. So for right now we tell you types of bonds that we find in there, but it's going to be important because your author just gives a very brief introduction to them, and it basically helps us distinguish between the two different classes of compounds, those being ionic compounds and molecular compounds. Now this distinction is important, and it's important because we are going to look at 5 different sets of naming rules. And on those 5 different sets of naming rules that we look at, the rules will depend upon whether the compounds are ionic compounds or whether they're molecular compounds. And if you can't distinguish between them, then you're not going to have any success in naming. So even though this seems like the most mundane, boring thing in the world, it's going to be the most important thing to your success in naming these compounds. Now the main classes of compounds that we'll look at are these here. And we're going to look at 5 different classes, as we said, and each class has its own set of nomenclature. They are binary ionic compounds, they're going to be ionic compounds with polyatomic ions, binary molecular compounds, binary acids, and then the 5th category will be oxyacids. So these are going to be the 5 classes of compounds that we'll name, and each class has its own set of nomenclature. So the way we name oxyacids is different than the way we name binary acids. The way we name binary acids is different than the way we name binary molecular compounds, and so forth. So again, each class here has its own set of rules for nomenclature. Many of them are related, but they're different. So let's look at, first of all, the terminology. We've already defined which words in here. Ionic and molecular. Okay, so we've defined these already. Remember, if it's an ionic compound that involves metals bonded with nonmetals. Metals and nonmetals would be for ionic. And if it's molecular, it would be nonmetals or metalloids. It's going to be basically anything over there on the right-hand side of the periodic table. Okay, we got some new words. Looks like the word that shows up here the most is binary. What does binary mean? Something that contains 2 elements. So these compounds will contain 2 different elements. It's a binary compound. Again, it will contain 2 different elements. So that means if it's a binary ionic compound, it's going to contain 2 elements, one of which is a metal and one which is a nonmetal. If it's a binary molecular compound, that means that it's going to contain 2 elements, but both will be nonmetals or metalloids. Now, we didn't talk about what an acid is. So an acid, we say, is this. We say that an acid have a hydrogen that is present and written at the front of the formula. Always. So acids have a hydrogen atom that is present. It is always written at the front of the formula. So a binary acid, let's underline it because now we're talking about acids. If it's a binary acid, it's going to contain how many elements? 2 elements, one of which is going to be hydrogen, and the hydrogen will be written at the front of the formula. Now, what do you suppose an oxyacid would also contain?
Oxygen at the end.
Yeah, it's going to contain oxygen, and usually that oxygen is at the end of the formula. So an oxyacid will also contain oxygen. And then, of course, the polyatomic ions, which here is in number 2. The polyatomic ions are ions that are listed on this sheet here that was passed out. They're ones that are going to involve metals bonded with nonmetals. And it will include one of these polyatomic ions. So again, each set has its own, each class has its own set of nomenclature. And in order to experience success with them, we need to be able to properly classify them. So what I'm going to do here is I'm going to write down some formulas. Start with H3PO4, HI, Na2SO4, Ag2S, SF6, and then Ti in parentheses C2H3O2 parentheses 4. I've written here now 6 different compounds. What I'd like you to do with these 6 compounds is to tell which class they belong to. So is H3PO4, is it a binary ionic compound? Is it a binary acid? Is it an oxyacid? Ionic compound polyatomic ion? Which one of these do each one of these fall into? So if you want to, just write down the number. If you think that H3PO4 is category number 3, then write down the 3 next to it. Just write it down and circle whatever number you think it is right next to each one. And so for the first one, let's get them locked in. We'll go once we get up to about 30 here. We're going to classify H3PO4 as one of the following: binary ionic compound with polyatomic ion, binary molecular compound, binary acid or oxyacid. So we'll count down: 5, 4, 3, 2, 1. And this here is an oxyacid. It's an oxyacid because it contains the element hydrogen written at the front of the formula, and it also contains oxygen, which makes it an oxyacid. Any questions on this one? Okay, so this here is number 5. We go to the next one. Classify HI as one of the following. Is it a binary ionic compound? An ionic compound with polyatomic ions? Binary molecular compound, binary acid, or oxyacid? And we'll count down: 5, 4, 3, 2, 1. This here's a binary acid because it contains how many elements? 2 elements. And written out front is hydrogen. If hydrogen's written out front, that makes it an acid. Any questions? Next up, Na2SO4 is which of the following? Is this a binary ionic compound? An ionic compound with polyatomic ion? Binary molecular, binary acid, or oxyacid? Let's get our answers locked in. We'll count down: 5, 4, 3, 2, 1. This is an ionic compound with polyatomic ions. Why can it not be a binary compound?
There's more than two.
It's more than 2 elements. But it's binary, remember it has to contain 2 elements. This here is showing how many?
3.
3 elements, exactly. And why is it not an acid?
Because there's no hydrogen at the bottom.
There's no hydrogen in there, so it cannot be an acid. Next up, Ag2S. Ag2S. Okay, let's get your answers locked in. We'll count down. 5, 4, 3, 2, 1. This is a binary ionic compound. Binary because it has 2 elements. Ionic because we have
Metal.
metal with a nonmetal. Metal with nonmetal means it's an ionic. If it's molecular, which type of elements are present?
2 metals.
Only nonmetals or
Metal.
metalloids. Silver is a metal. Next up, we have SF6. SF6. Let's get your answers locked in. And we'll count down. 5, 4, 3, 2, 1. This is a binary molecular compound. Binary molecular because it contains 2 elements. And it's molecular because both of these elements are nonmetals. They both sit up there in the upper right-hand corner of the periodic table. And then our last one. This is titanium acetate. Titanium acetate. It's actually titanium 4 acetate. We'll talk about how we name this. I guess we'll get to that probably tomorrow on this one. But we'll count down. 5, 4, 3, 2, 1. And this is an ionic compound with a polyatomic ion. Were any of you able to identify the polyatomic ion that is in there? Yeah, you haven't memorized them yet, but this is called the acetate ion. It's called the acetate ion. And so again, in order to succeed with naming, we have to be able to classify them into each of these different categories. So any questions on any of these here? All right, so this was number 3, this was the number 2. All right, so next up, we're going to get into the naming. And we're going to go through the categories in order. We're going to start first of all with binary ionic compounds. Binary ionic compounds. And we're going to start with one that most of us already know. That's this one right here. It is? Yeah, but what is its chemical name? Sodium chloride. What is its formula? NaCl. And again, its name is sodium chloride. Now, if we want to come up with a name for a binary ionic compound, here's how this works. What we say is that the metal retains its name, and the nonmetal retains its root name, onto which we add a suffix of IDE. So metals retain their names, nonmetals retain their root names, onto which we add a suffix of IDE. Now the root name is typically the first 1 or 2 syllables of the element's name. So if we look at something like sulfur, the root name of sulfur is sulf. And so if it's an ionic compound, we call it sulfide. If we find oxygen in an ionic compound, its root name is ox, and then we'd call it oxide in compounds. If it's bromine, it would be brome, and in compounds we'd call it bromide. So again, it's usually the first one or two syllables. This one here we keep two syllables. This is iode. So in a compound it would be iodide. Iodide. That's what you say when you have them, by the way. All right, this one here, phos. So it would be phosphide. Now you might say phosphide. That doesn't. I heard of phosphate, but never phosphide. But that's because phosphate is something else. It's not a part of a binary ionic compound. Because if it has ATE in it, as we mentioned earlier, if it has ATE, that means it also contains oxygen. So something that has an ATE suffix also implies that it has oxygen in it. So right now we're not going to worry about those that end with ATE. We're just going to worry about those that end with IDE. So if we then went to look at another one, let's say we looked at something like Al2S3, and we wanted to name this would be aluminum sulfide. Aluminum sulfide. Again with the IDE suffix. Ba, Br2 would be barium bromide. Barium bromide. Again with the IDE suffix. Na3N is going to be
Sodium nitride.
Sodium, pronunciation again?
Nitride.
Nitride, exactly. Sodium nitride is going to be this one. Again, if you've never heard of nitride, there are such things. Not as common though as nitrates, because remember nitrates you know about because they're the ones that are most commonly found in nature. They're the ones that also contain oxygen, but we're not looking at those right now. Now to go the other direction, we need a little more information. So for example, let's say we want to write the formula for something like lithium fluoride. Lithium fluoride. To do this, we need to know the charges that are on these ions. So remember that these are ionic compounds, and because they are ionic compounds, that means that they are made up of particles that have charges. So everything here in group 1A, all of the alkali metals, always have a charge of 1 positive. The elements of group 2A always have a charge that is 2 positive. And if we look at the metals of group 3A, over here, they are all going to have a charge of 3 positive. So in your A groups in the periodic table, the Roman numeral designates the charge that those ions have in compounds. Then, starting with group 17 on the side, or group 7A, the halogens have a 1 negative charge, the elements of group 6A have a 2 negative charge, and the nonmetals of group 5A have a 3 negative charge. And again, this 3 negative will only apply to the nonmetals of this group, not to the metals of this group. So we talk about the charges. One thing that is always true, metals always have a positive charge, nonmetals always have a negative charge. Always in compounds, metals are always positive, nonmetals are always negative. And that's because when we go back to how we define these, we say that in ionic compounds, electrons are transferred. And electrons are always transferred from metals to nonmetals. And when electrons are transferred, that means that metals tend to give up the electrons. And remember, electrons have what type of charge?
Negative.
They have a negative charge. The electrons have a negative charge. So if we subtract the negative, that gives us something that is positive. That's the way the math works, right? You subtract the negative, you wind up with a positive. So that's why metals always have a positive charge, because we're taking electrons away from them, and they wind up with positive charges. Nonmetals, on the other hand, these tend to gain electrons. And because they gain electrons, when you add a negative, you wind up with a value that is negative. So that's the way that the math works on that. Now, the other ones we're not defining for right now. That we'll get to in just a bit. These here have some other set of rules. Group 14 here has another set of rules with it. So right now we're just going to look at these. So now when we want to write a formula for something like lithium fluoride, we find where they're located on the periodic table. Here's the lithium, here's the fluorine. We see that lithium would have a charge of 1 plus, fluoride a charge of 1 negative. The idea in compounds now is to balance charges. We want the total of the positives to balance the total of the negatives. So right now with the 1 positive and 1 negative, we can say that these charges are already balanced. And because they're already balanced, and here's how I'd go ahead and write that out. We have Li with a positive charge, F with a negative charge. We then wind up with a formula of LiF. And that's it. If we then looked at something like sodium sulfide, we then look these up on the periodic table. Well, we're looking them up today. You're going to have them memorized. But sodium sits here. Its charge is 1 positive. Sulfide is going to be 2 negative. So again, we come back here. We have Na with a positive charge. Sulfide is S with a 2 negative charge. Now we need to balance charges. They're not balanced. Which one are we deficient in?
Na. Sodium.
Sodium. So how many sodiums do we need to balance the charge of the 1 sulfur? 2. So we could show it like this, that there's 2 sodiums for every one of the sulfide ions. The formula we write then is Na2S. We write it as a subscript. And these subscripts are a count of the number of atoms of each of that particular type of ion. Now, you may have had a lenient high school teacher that would say, well, if you leave charges in here, that's okay. It's not okay. That's not the way that we write those formulas. If you leave charges in the final formula, it's wrong. It will be marked wrong by Master Chemistry. It will be marked wrong by me on an exam. So final chemical formulas are always written without indication of charge. Let's try another one. Let's try strontium iodide. Strontium iodide. We go back to the periodic table. Where is strontium? Its charge is going to be, darn, we just had that element quiz.
2 plus.
Right, it's 2 plus. It's right here. Iodide is where? Group 17. So its charge is going to be 1 negative. So we have strontium with a 2 plus charge. We have iodide with a 1 negative charge. Now to balance charges, we need more of which one? Iodide. How many more?
2.
We need 1 more. So with 1 more, we now see that the 2 positives balance the 2 negatives. The 2 positive balancing a 2 negative. The formula is SR I2 is the way we'd write that formula. Let's try another one. And if you have any questions, raise your hand. Otherwise, we'll just keep doing some examples here. Next up, we're going to do magnesium sulfide. Magnesium sulfide. For magnesium sulfide now, we look up magnesium. Charge on magnesium is 2 positive because we find it here. Sulfide is going to be 2 negative. So we have Mg 2 positive, S 2 negative. What happens to charges here? They balance out, they cancel out. So the formula is simply MgS. Again, the final chemical formula is always a count of the number of atoms. Ones are implied, we don't write subscripts of 1. Likewise, we don't write charges with the number 1. We just write a simple negative or a simple positive to show a 1 positive or 1 negative charge. Now, if we try something like aluminum oxide. Aluminum oxide. We go to the periodic table. We find aluminum. Aluminum is going to have a charge of 3 positive. Oxide is 2 negative. So we come back here. Al with a 3 positive. Oxide 2 negative. So now we need to think about this a little more creatively when we balance charges. And one of the ways we can think about it is to calculate what's called a least common multiple. A least common multiple. And we just look at the whole number values here. What is the least common multiple between 3 and 2? It's 6. So what we're going to try to do is we're going to try to wind up with 6 positives and 6 negatives. How many aluminums do we need altogether to get 6 positives? And how many oxides do we need to get 6 negatives? Right, so you think about it like this. We now have 6 positives balancing 6 negatives. So then when we write the formula, we'd write it as Al2O3, where again the subscripts are a count of the number of atoms of each element. There's 2 aluminums balancing 3 oxygens here in that formula. So any questions that you have on these examples? Okay, let's try these. Li2S, Ca3N2. We'll try potassium phosphide. And we'll try barium oxide. And then these are the 4 that you need to be able to do for sure. But I'll give you a couple challenge problems. If you can't get the challenge problems, that's okay. But go ahead, if the formula is given, write the name. If the name is given, write the formula. So we'll give about 10 more seconds here. If you don't have it in, that's fine. Just go on to your next one if you are still working on them. We'll count down. 5, 4, 3, 2, 1. Lithium sulfide, very good. Next one. The name of the compound that has a formula of Ca3N2. Ca3N2. We'll count down. 5, 4, 3, 2, 1. All right, calcium nitride. Very good. Next up, we have potassium phosphide. We're going to give the formula of potassium phosphide. This one might take you a little while longer because remember you do need to look up charges. And we'll count down. 5, 4, 3, 2, 1. K3P. Wonderful. Great job. It's K3P because the charge on potassium is how much? 1 positive. The phosphide is going to be 3 negative. So with a 1 positive and a 3 negative, we get the K3P. Next up, let's try the barium oxide. Barium oxide. We'll give you about 10 more seconds here. And then we'll count down. 5, 4, 3, 2, 1. Great. BaO. BaO because barium is Ba with a charge of 2 plus. Oxide is O with a charge of 2 minus. So if we have a 2 plus and a 2 minus, they cancel out, and the formula is simply BaO. Bonus problems. Anybody get the bonus ones?
And find Ka. Oh.
BaNa2. Anybody get this one?
Bariums.
All right. Well, let's look at where they are in the periodic table. We have Ba, which is a charge of 2 plus. Sodium, a charge of 1 plus. It's a bonus because this one is not possible. Why is it not possible? You can't combine a metal with a metal, so it doesn't work. Of course, if you want a night job, you could call this one a banana. All right, very cool. And this one here, I know. See, I was young one time, and I was cool. I get old, and I'm not cool, but whatever. That's all right. Anybody know this one? Now this one's a lot more fun if you just read the formula. Let's just read it together. K9P.
That was a 9.
Also known as this. Isn't this great? 8 in the morning? It's actually 9 o'clock now. You guys should be more awake. Also known as dog urine. How about that? Okay, any questions?
Sometimes look like eggs.
Gosh, you guys have no sense of humor whatsoever. Okay, next up. Not where I got it from my dad. And he was not very funny until I got older, and then I realized how much I appreciated his humor. All right, what we're going to look at next is we're going to fill in the periodic table in these places that we left off for the time being. And for the ones that we left off, turns out that these will have multiple charges. If we look at the transition elements, and I'm going to put this in black, we say that these here have multiple charges, or variable charges. And because they have multiple charges, we can't look at the periodic table and say that iron is always going to have a 2 positive charge, or the iron is going to have a 3 positive charge. So what we do is something like this. In the case of iron, we would say that there's 2 different forms of iron. There's iron 2 and there's iron 3. And we write them with Roman numerals. We say that iron 2 has a 2 positive charge. Iron 3 has a 3 positive charge. Likewise with copper, let's see if we go the reverse direction. What do you suppose we call this first one? Copper 1, and we call this one?
Copper 2.
Copper 2. And then we need to be able to write Roman numerals, so copper 1 would be written like this, the Roman numeral 1, and copper 2 then would be written like this. Now there's no need to memorize what the possible charges are, because if you see the name of a compound, the name of the compound will already contain its Roman numeral. And then going in reverse direction, if you see the formula, you should be able to figure out what that Roman numeral is in the name. Now, we use this method of nomenclature. Compare it with the older form of nomenclature. In the older form of nomenclature, we would have called the iron 2, this would have been called the ferrous ion, and this one here would have been called the ferric ion. In the old system of naming, this one would have been called the cupric ion. This one here would have been called the cuprous ion. Okay, so in the old system of naming, we would have used these. The downside of using these, and I think I have these wrong. I do. This one is cuprous, and don't worry, you don't need to know these anyhow. I'm just showing, though, why we don't use this anymore. The reason why we don't use it is because when there used to be multiple charge ions, we would use the one that has the lowest charge. We'd have it end with an OUS suffix. The one with the highest charge would end with an IC suffix. The problem with that is that here, cupric had a 2 positive charge. Here, the ferric had a 3 positive charge. Whereas if you compare these two, which had the same charge, one had an OUS suffix, one of them had an IC suffix. And because of that, then, you pretty much had to know all of the possible charges there were, not only which ones had multiple charges, but you also had to know what the possible multiple charges were on these ions. So today, when we look at them, where are we going? Here we go. All you need to know is that these elements here have multiple charges. And if they have multiple charges, the Roman numeral will be given in its name, or if we see the formula, we'll be able to figure out what that charge is by working backwards. Now there are some exceptions to it, and here are the exceptions that you need to know. First of all, these elements here, and I'm going to put them in blue. These elements here, even though they are grouped together with the ones that have multiple charges, these here have a single charge. In other words, these do not have multiple charges. However, even though they do not have multiple charges, if you go back to your list of common polyatomic ions, you'll see that these are the common metal ions that you are to memorize. So those 3 that do not have variable charges of the transition elements, those are on your to memorize list of common metal ions. Okay, so any questions on that? You look at your common metal ions here. The common metal ions, cadmium, silver, and zinc. Those are the 3 of them here that do not have variable charges. All of the rest of the transition elements do. In addition, and I'm going to keep the coloring consistent here, these elements here, this block right here, also has multiple charges. So not only do these have multiple charges, the transition elements, but this block over here has multiple charges as well. Which means when these elements are used in ionic compounds, we must also include the Roman numerals. So Roman numerals are included for this block here, and they're included for all of these here, except for these 3. Yes, when?
What about aluminum?
Aluminum is identified by its 3 positive charge.
Okay.
So when we talk about the 3 positive charge, it's pretty much really only applying to the aluminum in that group, because that's the only metal that's outside of this box of variable charges. What's that? B is a non-metal, and it is not found very commonly in ionic compounds. So we're not going to worry about boron. Anybody else? It's not something I'm going to trick you on. It's not going to be something that you're going to see your author giving you a problem with it in there, asking you to identify it, because again, it is a non-metal. So then when it comes to writing out names for these. Let's say we had something like iron 3 oxide. And we wanted to write its formula. To write the formula of iron 3 oxide, we then look at the Roman numeral. This Roman numeral tells us that the charge on the iron is going to be 3 positive. Oxide then, based on its position in the periodic table, is going to have a charge of how much? 2 negative. So I put an oxygen with the 2 negative. Now what we need to do is we need to balance charges. We have a 3 and a 2. The easiest way to do this is to find the least common multiple between 3 and 2, which is 6. So how many irons do we need all together to get 6 positives? And how many oxides do we need to get 6 negatives? 3 of them. So now our charges are balanced. When we write the formula, we write it as Fe2O3. And this then is a formula for iron 3 oxide. Let's try iron 2 oxide. We try iron 2 oxide. That means we're dealing with iron, which has a charge here is going to be 2 plus, because it's the Roman numeral 2. Oxide's charge doesn't change. Its charge is 2 negative. So we have a 2 positive and a 2 negative. What happens to charges? They cancel out. And the formula for iron 2 oxide is FeO. Now what's important to realize is what this Roman numeral stands for. This Roman numeral stands for the charge. The Roman numeral stands for the charge. It does not stand for the number here in the formula. What it stands for is the charge of that particular ion. So if we did another one like this, let's say we did something like titanium. Let's do titanium. See how many people know this Roman numeral. That'd be Roman numeral number 4. Let's do titanium 4 sulfide. Titanium 4 sulfide. So in titanium 4 sulfide, that means titanium would have a charge of 4 plus. Sulfide would be S, and its charge is going to be 2 negative. And I'll be careful here. We need to find the least common multiple between 4 and 2, which is 4. How many titaniums does it take to make 4 positives?
1.
And how many sulfides to get 4 negatives? 2 of them. So again, we're just trying to balance charges. Formula then becomes TiS2. There's 1 titanium and 4 sulfurs. If we went in the reverse direction, let's say we had something like CuO and Cu2O. CuO and Cu2O. Well, now we look at these and we know that both of these contain copper, but looking at our periodic table, we know that if they contain copper, it must have a multiple charge. If it has a multiple charge, that means when we write its name, it must have a Roman numeral in its name. So this is going to be copper, some sort of Roman numeral. Let's not say it right now, but it's going to end with oxide. And this next one's going to be copper. It's going to have some sort of Roman numeral and oxide. Figure out what those Roman numerals are. This particular one, the first one is going to be copper 2 oxide. Where are my 2's going? Sometimes after I stop for a while. This is copper. First one is copper 2 oxide. The second one is going to be copper 1 oxide. And that's because oxide always has a charge of 2 negative. So if this formula has 1 atom of each, that must mean it's being balanced with a charge of 2 positive. If we have a 2 positive and a 2 negative, that gives us this formula right here. This charge of 2 positive gives us this Roman numeral. In the second one, oxide always has a charge of 2 negative. So that must mean that copper here would have a charge of 1 positive. It's going to be 1 positive because if we look at the formula, there's 2 different coppers in there. And those 2 coppers have to be spread out over 2 atoms. That must mean that each atom has a 1 plus charge. It's that 1 plus charge then that gives us a Roman numeral of 1. Alright, I think we're pretty much out of time here today. Let's see how we did on this last one. It is chromium 3 bromide. So where we will be starting on Tuesday. Now, worksheet. I did give a worksheet out. This worksheet is not going to be anything collected. In fact, you will not be able to name all the stuff on here yet. However, answers are up on the D2L content section. You will not be able to complete all of this until after our next class. You must have this other handout memorized though by Tuesday. We'll start with this right away on Tuesday morning.